8 parts ago, a kernel launch was an unchecked guess. You wrote one line, hit run, and mostly just hoped. This is the last video in the series, and there is no new technique to learn in it. This one only names what comes after the course. Welcome to the epilogue, where to go next. This closer has 2 jobs. Name what you now own plainly, then map what is still ahead. Let's start with what you built. Now you can read the machine, write it, check that it is right, and measure whether a change actually helped. That is the discipline this closer names. You did not just watch 8 parts. You built a working method for GPU programming, and that method is what the rest of this closer makes explicit. First, what you now own, the whole method, gathered in one place across all 8 parts. Second, the map beyond it, real things this course names but never taught, and why each one had to wait. 1. You can read the machine, the roofline and arithmetic intensity that tell you whether a kernel is memory-bound or compute-bound, threads, warps, streaming multiprocessors, and how the GPU hides a weight by switching to other ready work. 2. You can write a kernel and move data on purpose. The launch syntax, allocating and copying device memory, and striding across an array bigger than your grid. 3. You can trust the result, catching errors with a check macro, running the sanitizer on a buggy kernel, and verifying with a tolerance instead of exact equality. 4. You can move less data faster, the memory pyramid from registers down to global memory, shared memory, coalesced access, and bank conflicts. 5. You can cooperate safely, barriers, atomics, a correct reduction, a scan, and warp shuffles. 6. You measure instead of guessing, n-site systems for the hotspot, n-site compute for the Y, and the loop of profile, fix, and measure again. 7. You climbed a real ladder, naive matmul, then coalesced, then shared memory tiled, then thread tiled with CUDA C, the vendor library, measured on top. Before this course, launch it, hope it's right, guess why it's slow. Now, launch it, catch the error, verify the result within a tolerance, profile the real bottleneck, and change one thing at a time. A kernel launch used to be an unchecked guess. It's a checked, measured step now. None of what you built is the ceiling. Part 8 measured CUDA C taking a Tensor Core path to beat the FP32 ceiling, measured there, not taught, and they are one item on a much taller stack. Every kernel you wrote here is ordinary CUDA C or C++, running one at a time, and Part 6 and 8 added library calls on top. A taller stack sits above all of it, newer hardware features, and a whole software layer written against CUDA. We're naming that stack now, so you know exactly where the durable ground under your feet ends. 5 stops now, all from low-level CUDA performance work. Every one of them builds on a kernel you can already read. None of them is taught in this course. CUDA streams are how you ask for an independent copy and an independent kernel to overlap in time, instead of running one after the other. Whether they really overlap depends on page-locked host memory, asynchronous copies, and what the device supports. Tensor Cores are hardware units for matrix math. WMMA is one CUDA C++ way to reach them. A whole warp computes one matrix multiply fragment together, instead of one thread per output. It needs Volta, SM70, or newer. cp.async is an asynchronous way to load data into shared memory. It needs Ampere or newer. On an older GPU, it simply is not there. These are 2 separate features. TMA moves multidimensional tiles between global memory and shared memory asynchronously. Fred block clusters let the blocks in a cluster read each other's shared memory. That is what distributed shared memory means. Both need Hopper SM90 or newer. Producer consumer GEMM is a kernel design pattern, not a single call. Some warps fetch tiles while other warps do the math, and the fetch is staged with cp.async or with TMA, depending on the design. 5 stops on the map. The ones tied to a GPU generation are labeled with it, and none of them are taught here. 3 more names. From the layer above CUDA C, these all move fast. Triton is its own language and its own compiler for writing GPU kernels. You write it in Python. You do not write it in C, and you do not write it in CUDA C++, though on an NVIDIA GPU it still goes through CUDA underneath. PyTorch extensions let you write a custom CUDA kernel and plug it straight into one specific framework's build. FlashAttention is a family of attention kernels built on this course's own memory discipline, what its authors call I/O awareness. It tiles the work and fuses attention's own steps into one pass, so the big score matrix never has to travel out to memory and back. The application programming interfaces here move fast. Check the kind documentation before you build on any of them. This is exactly where they move fastest, and that is exactly why the course taught the durable layer underneath it first. It is easy to assume real GPU programming is whatever framework is trending right now, but the library and DSL layer above CUDA C moves fast, new names, new application programming interfaces, sometimes new tools, inside a matter of months. CUDA C, the SIMT model, and the memory hierarchy have stayed stable for well over a decade. Everything named in this closer still rests on that same execution and memory model, even when its interface looks different. That's why this course spent 8 parts on the foundation, and not on whichever framework is new. The green box is what you own. Reading the machine, writing and verifying a kernel moving data, and then measuring it. The blue box is named, but not yet yours. Streams and Tensor Cores, cp.async, TMA and GEMM patterns, and the Triton, extensions and FlashAttention layer above them. Same idea as every boundary this course drew. Know exactly which side of that line you're standing on. You can read a kernel's memory traffic, catch its bugs, coalesce its access, and profile it instead of guessing. You climbed a real ladder from a naive loop to a kernel that respects the hardware. That's not a small thing. It's yours now to keep building on. Go write some CUDA.